So in regression, we are trying to find a relationship or more variables. We'll take a small example here just to understand. So you all are in third year of your engineering, and when you are giving examinations and getting results, there's something as what you earn is CGP. Okay, and also you know that we conduct a test called as, let's say, an AMCAT. Okay, so it's basically a test for aptitude. Want to check the aptitude of the student from a placement perspective. Now, I want to establish, is there any relationship between the CGPA and AMCAT score? Okay, so AMCAT takes aptitude test as well as programming test. So I want to understand whether there is any relationship between CGPA and AMCAT score. A relationship of the form that, let's say, if CGPA is higher, whether the AMCAT score is also higher. If CGPA is lower, whether the AMCAT score is low. So I want to find this relationship. So for that, what I'll have, I may have, let's say there are 1,000 students or 1,200 students or 2,000 students or 3,000 students in the institute giving the AMCAT examination, and I'll have a data frame like one column of CGPA and another column of AMCAT score. Okay. Okay. And let's assume that the CGPA is out of 10, the max, and AMCAT is out of 100. Okay, the AMCAT is out of 100. So I have this data frame. Let us say there's a GR number as one of the key or index. We'll have such kind of a data frame where for a particular GR number, okay, I will have, let's say the CGPA is, let's say 9.6, and I want to know what is an AMCAT score. Okay, so let's say this fellow has an AMCAT score of 82, so on and so forth. I have this data for, let's say, for odd 1,000 students. Now I want to find a relationship among these two. Whether it's a directly proportional, inversely proportional, or there's no relation at all, whatever it is. So I want to establish a relationship. Or if you recall hypothesis chapter, I'll say that no, the hypothesis is that higher CGPA has higher AMCAT score. Okay, higher CGPA, higher AMCAT score. Okay, so this is the hypothesis. Now I want to verify whether this hypothesis is true or false. Okay, so whether there is any alternative hypothesis that is exists to this particular hypothesis. So in this case, in the example of CGPA and the AMCAT score, X is nothing but the CGPA and the AMCAT score is nothing but Y. Okay, so we are trying to fit a model now. So with respect to the model, AMCAT score is Y, and there's a function that connects X to Y. Now, in terms of regression analysis model, X is called as the independent variable. X is called as a independent variable. And Y is called as dependent variable. Y is called as the dependent variable. So X is a independent variable, and Y is a dependent variable. So a model is basically connecting or using the independent variable values. The model will predict the dependent variable value. The model will predict the dependent variable value. Now, the most simplest form of regression analysis is simple linear regression. Okay, so the most simple is simple linear regression. So in simple linear regression, it is simple linear regression. Now, a simple linear regression is a model where model is denoted using an equation of the form, let us say a plus bx, or we could write it as y is equal to mx plus c, a typical equation of the straight line. Okay, so whatever model we build, that model is a straight line model. The requirement of simple linear regression is that this dependent variable is should be continuous. Okay, should be continuous variable. The continuous variable, and 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 x is the independent variable. X b is the slope of the line, and a is a constant. Okay, a is the constant. Now, the example that we had considered earlier of CGPA and this AMCAT scores is of this form. There, the CGPA. So we could have an equation of this form, that y, that is an AMCAT score denoted by, could be m into CGPA plus c. Okay, so this AMCAT score and CGPA model is a simple linear regression model. So what does we? So if you remember that data frame that I had shown you in the earlier slide, so we may plot a scatter plot where the x-axis will be obviously an x variable. So this is CGPA, and y-axis will be the AMCAT score. Okay, the AMCAT score. And let's say we have data for 1,000 students. So what we'll have, value will be on the x-axis will be on the range of 0 to 10, because that's the CGPA pointer. The value on y-axis will be in between 0 to 100. Okay, will be in between 0 to 100. And on this graph, we may plot 1,000 points, scatter points. Means what? For a particular student, we may have a CGPA of, let's say, 9. And he may have a score of, let's say, 72 or 70. So we'll have a cross point. You have a crowd of many cross points spread over this particular graph. Okay, because it will be CGPA versus, and there could be some kind of a correlation, some kind of an. So what we want to find is how do we model the line. So now, suppose what is prediction here? Suppose there's a data set of 1,000 students, and among those data sets, there is one CGPA, let's say 8.41. Okay, no, there is no student available with score 8.41 among the 1,000 students. You want to know that if a student had a CGPA of 8.41, what could be his AMCAT score? How do you predict this? And for that, you need a model. Okay, for that, you need a model. So the simplest model is having only one dependent variable and one independent variable. And what is the requirement? That the independent variable should be 1 and the dependent variable should be continuous variable. Okay, so it should be continuous in nature. Now the question really comes in is that if I want to model this, if I want to fit a model for these points, okay, so there are, means I want to draw a line, straight line, maybe of this fashion. So this is my model. But how do I determine, is this the best model? Okay, or is this the best fit line? So the reason is that the line could pass, there could be another line that could pass this way, there could be another line that could pass this way, there could be another line that would pass this way, line that will pass, let's say, this way. So there could be multiple lines I could draw, different slope values, different values of m. Now, how do I determine which one is the best line or which one is the best fit? So determining fit is the requirement. Okay, determining the best fit is the requirement for any regression model. So how does the best fit really works, or how does the best fit is determined? So to determine the best fit, let's go to a small example. Suppose instead of going with a complex example, suppose we have some, let's say, graph. Okay, so we'll keep it small, simple, and we'll say that our mx plus c line, line passes this way. Okay. So what does this mean? First of all, let's understand this. This green points are observed data. The green points are observed data. So let's name it as y. Sorry. So green points are the observed data. So what does the observed data really mean? That on the x-axis, this will be, let's say, 0 to 10. What does this mean? That if a fellow with having a CGPA of 1 had also had an MCAT score of, let's say, 10, there is one such case. There's another case that a fellow having a CGPA of, let's say, somewhere here, 1 point something, let's say 2, for that matter, had an MCAT score of, let's say, 7. Okay, and an MCAT score of 7. So 7 is the observed value. Okay, so you have a data for it. 7 is the observed value. Suppose there's a student with CGPA of 4 and this value is also, let's say, around 4. Okay, then there's a fellow with, let's say, CGPA of 7, but the score is of, let's say, 2. Now means 40, 70, let us say 20. Okay, and there are two more students. So there's a student with CGPA, let's say, 8 and a score of around 90 or 85. And there's a student with 9 CGPA, let's say, and a score of around, let us say, 60. So for those data points, you have given a line, a fit line. You have drawn one line. Now you want to determine whether this line is a best fit line or not. To do this, what is done is, so there are 2 points now. The points that fall along the line, they are called as predicted points. Okay, so let's name it as YP. It will be equal to MX plus C. And these Y points shown in green are observed points. So you have that data frame. Okay, so there's a X value and there's a Y value. There's a GR number. Okay, and you have this CGPA of the student and you have the observed MCAT score obtained from the database. Now, what is done to understand, and then there's a possibility that you could fit multiple lines, but you need to understand whether this line is best fit or not. So what you do is you that here for CGPA of 2, the model says that the score will be around 20. That is what the model is saying. But actually the student has got 70 marks score. So there's a difference between what is an observed value and what is the predicted value. So there's a difference, and that difference between predicted value and observed value is called as residue. Okay, it is called as residue. So we can have residuals for, so here in the first point the residual is very minor. Third point the residual is very minor, but fourth point there is a residual. Fifth point there is a residual. Sixth point there is a residual. Means, let's say for the last point with CGPA of 9, the model says that the score is exactly, but actually the student has scored 60 marks, and so forth. So you have residuals, but these residuals could be positive, could be negative. For example, here it is negative because this value is smaller on the line, on the yellow line, and the green point is bigger. Positive. So what we do, we take summation of predicted value minus observed value square. Okay, so if it is negative, it will become positive, and this is called as residual sum residual sum of squares. Okay, residual sum of squares. Now, as an experimentation, I could fill multiple lines. Means I may have yp is equal to m1x plus c. I could have yp is equal to, let us say, m2x plus c. Let us say it is fitted this way. Okay, I have yp is equal to y3x m3x plus c, a different slope. Okay, so it could be, let's say, this way. Okay, I may have yp is equal to m4x plus c, and so this could be this way. So there could be multiple lines I could draw. Now, which line I should consider as the best fit is the line which gives me minimum residual sum of squares. Minimum residual sum of square. That line will be best fit line. Okay, that line will be best fit line. So a line which has minimum residual sum of square will be my best fit line. Our fit line may start at some initial position. Let's assume this way, and during each iteration, it may start moving to a possibly a best fit position. Okay, after many iterations, it may start moving. It may come or will come up to a best fit position. Now, this iterations will ensure that every time the slope, during every iteration, the slope changes. And how does the slope will change? It will change based on the residual error or sum of square errors. And then when the sum of square error is minimum, that line will treat it to be best fit line. So during each iteration or epoch of learning or iteration of learning, the slope will change. Okay, the slope will change. So the slope m will be changing by, so we want to correct the slope m. So it could be plus or minus, okay, plus or minus a derivative of the slope. Okay, so you want to have, or plus or minus, we can say it's a derivative. So let's say it is delta m. Okay, sometimes the delta m may be positive, sometimes the delta m may be negative. So during each iteration, there will be change in m's value, and when this delta m remains constant and we cannot optimize anything in m, then we can say that we have reached to a best fit line. Okay, we have reached to the best fit line. So if I first case, that is where the delta m alpha is very small, the learning rate is very small, what will happen in the first case? If I plot this graph against slope, okay, against slope and the cost function, slope and residual error or the cost function, that is residual errors, then if it is a gradual change, the purpose of doing this exercise, that is purpose of doing this exercise, that is optimizing m, is basically trying to find a global minima. Okay, trying to find a global minima means you want to find such a value where the residual error, this residual y-axis is minimum. Minimum means 0. Okay, you want to find such value of m where y-axis is 0. So if at the initial start, if this alpha is small, what will happen? That you may gradually start going this fashion towards 0, and after hitting 0, it may start increasing. Okay, so this is the plot of residual errors of cost function against M. So this kind of a plot will tell you that, oh, so at this point you get a global minimum. So this is a value of M, which is a best fit. And this kind of a curvature or finding global minimum is called as gradient descent. Okay, what does this mean now? Is that I will plot, I'll get M1, M3, Mn values, and for each of these M1, M2, M3, Mn values in this above figure, I'll get residual error also, that is cost function. And then I'll plot a scatter plot of cost function against the slope, and I'll get different values, different errors or different error values for different M values. So whenever the cost function is 0, means there is no error. So predict, so every observed point and every predicted point is one and the same. That is when the error will be 0. So if that is my best fit, will be global minima. Global minima means the cost function or error should be 0. So that will be global minima. So when every predicted point and observed point will be 0, that is my best M value. That is, so this is what we are trying to do. But when, if the alpha is very higher, then what will happen? That from this M value, I may jump straightway here. The next point could be this. From this M value, I may jump here. From this M value, I may jump here. So I'll not get a gradual change and my algorithm. So I'll get different lines, fit lines of different slopes. They will hop drastically in different directions. Okay, and that's why alpha is kept to be smaller. But too small alpha means too large training time for the algorithm. Too large alpha will not great impact on. Try to put this model as a regression model. What will happen to this? What the price denoted by y will be 1, and there will be these features ax1 plus bx2 plus cx3 plus dx4, so on and so forth, plus the epsilon, that is the constant. And this is called as multiple linear regression. What does this mean? That you have multiple independent variables and one dependent variable. So this is called as multiple linear regression. Now, in this multiple linear regression, there will be multiple features comprising of or representing the independent variables. So all these factors are independent variables, and this is the cost, okay, which is a dependent variable. So in simple linear regression, what we have is only one independent variable. In a multiple linear regression, we have multiple independent variables.